I'm not saying it's aliens, but we have to talk about, and we can talk about this video that was released in the House of Representatives in some committee meeting. So this shows a video. Let's look at this video right here. This is a video from a drone looking at an unidentified aerial phenomenon. I think that's what it's called. And so that's that orb in the middle of the screen. So this is from a drone tracking it. I don't know everything going on here. I'm not a weapons expert or anything like that. But let's say that, let me get over this. Let me move that around. Where's my video? There it is. Okay, pause that. Okay, so here's the orb right there. And then there it is impacted with a hellfire missile right here. Here it comes. I don't know why they said, hey, look, we don't know what this is, let's shoot it. I mean, I guess that is what humans do. But I think this offers an excellent opportunity to look at the physics of a collision and find out what we can learn from this. So there's the missile, it collides and reflects off. And then there's a bunch of stuff going on with this orb. I'm calling it an orb. It's an UAP, unidentified aerial phenomena. So, one of the things in the past, a lot of these things were like, hey, it's just an optical effect. This is not an optical effect, right? That missile impacts the orb, and there is a result. There's not an explosion, because apparently these are like non-explosive missiles. Okay. So what I want to do is to use this video, make some assumptions, use video analysis to get velocities, and use that to find the mass of the orb. And that's what we're going to do. We'll do a bunch of stuff, but that's what I want to do. Okay, so I put this little next slide in here because I would forget. So let's talk about conservation of momentum and how we can deal with this situation, because it's clearly not easy, right? Because the reference frame is moving. So how do we deal with that? What do we do with these kind of things? So why is momentum conserved? Let's switch to the board right here, and then we'll talk about that. So here we have the orb, and it's traveling that way. And then this missile comes in this way. And then it collides off that way, and that goes that way. So the first question is, when is momentum conserved? So remember that, let's call this the missile, and this the orb. And let's say during the impact, I'll put it right here, then there is a force, sorry about that, there's a force from the orb on the missile, and then there's a force on the orb from the missile. So it's two forces. Interactions have two components, right? They're an interaction between two things. Now, what do forces do? The net force on an object, F object on the missile, is equal to the change in momentum of the missile with respect to time. And the same thing's true for the the orb. The net force on the orb is the change in momentum of the orb with respect to time. Now, if they only have those two forces acting on each other, and I know that this is negative the force of the orb on the missile because of Newton's third law, and the times are the same, then that means delta P orb is equal to negative delta P missile. That's what we call conservation of momentum. So momentum is conserved if that's the only force, which clearly is not the case here, but over short time intervals, it's kind of the case. How can we use that to find the mass? So the first we could write this as just the change in momentum total is 0, or the initial momentum, I'll call it 1, is equal to the final momentum 2. Those are all the same thing. In this particular collision, we know what that missile is. And we know the mass. It's a 46 kilogram, let's say 46 kilogram missile. I don't really know. I'm not a weaponologist, so I just looked it up. They give the length and they give the max speed, and that's another problem that we need to deal with. But this is how we have conservation momentum. Okay, now we have two problems to deal with. Number one, we are looking at the motion of the objects from a moving reference frame. So that's the camera looking at the two objects as they move. That doesn't matter, right? We could be in two different reference frames like this. Here's one that's moving with some velocity of the frame, and this one's the velocity is at rest. It doesn't matter which frame I measure my velocities in, as long as they're an inertial reference frame, because Newton's second law works in an inertial reference frame. So it doesn't matter if it's a moving reference frame. Momentum's still conserved, right? The values of momentum aren't the same, but momentum is still conserved in a moving reference frame. So that's fine. We can use the reference frame of the orb where it starts off in 0 meters per second in that reference frame. It's fine. Okay. Now, the other problem we have is if I want to use this to calculate the mass, in a moving reference frame, I actually don't know from the video the velocity of the reference frame. So I don't know the velocity of the missile. I don't know the scale of the missile. I don't know the scale of anything, because what we're going to do is use video analysis. So in video analysis, you take the frame, and then I have some object right there, and I can mark the location of that. And then here's my next time frame, and maybe the object's over here, I mark the location. So I get XY position, and these are my times in each frame. But in order to get XY position, I need to know, how wide is the actual frame? What's the scale of the video? And in this case, I don't have a scale. You can see that Hellfire missile, which is, I wrote it down, 1.6 meters long, but now we're at a very, very tiny part of the screen that we're scaling the whole thing. It's kind of hard. But it turns out that we don't need to know the distance scale. We can use any distance scale, and I'll show you why. Okay, so let's set up our conservation of momentum equation up here. So here I have the missile, and here's my orb. And so this has a velocity, I'll call it V missile 1. It's the velocity of the missile before the collision. And the velocity of the orb before the collision is 0. It's at rest in this frame. And then this missile bounces off over here. So this is V missile 2. And then the orb goes over here, V orb 2. Conservation momentum says the following. It says the momentum before is equal to the momentum afterwards. So, this is the mm. And this is the orb. It has a mass MO. So mm v m1 plus 0, because it has no velocity there, is equal to mm v m2 plus mo v o2. Right? That's the momentum before the collision. That's the momentum after the collision. Now, I know the mass of the missile. I know the mass of the missile. I don't know that. So let's solve for this. So I get MO VO2 is equal to MM VM1 minus MM VM2. And I can factor out the mass. MM VM1 minus VM2, like that. Now I can, could I solve for the mass? Could I solve for the mass of the orb by dividing by the velocity? No, you can't, because that's a vector. That's a vector. But I can write this. If this is a velocity in the xy direction, I'm assuming we're looking at this overhead. Those are velocities in the xy direction. So I can write MO VO2x is MM VM1x minus VM2x. I can also write MO VO2y is MM VM1y minus VM2y. Those are scalar equations, and I can solve for those. So this gives me over here MO is equal to MM VM1x minus VM2x over VO2x. Now, there's a couple important things here. One, I can solve for the mass. So if I know the mass and the velocities of the stuff before and after the collision, I can find the mass of the orb. We're looking at how much recoil does that orb have, and that tells us something about its mass. It's kind of cool. It's kind of like what they did with that DART mission, where they hit an asteroid with an object. Same idea. Very similar, actually. But the other very important thing here is that I have mass, if I know the mass in kilograms, and the velocity in meters per second, meters per second, meters per second. The units for the velocity cancel. Okay, so that means I can use unknown velocity units. As long as they're all in the same units, it doesn't matter. So I don't have to scale the video. I can just do it, right? I can just, even if I pick the scale of the video using my hellfire missile, which is probably a bad estimate, I can just, it doesn't really matter. As long as the scale doesn't change throughout the video, which I'm not really sure, then I can do that, okay? So I can do that. I can do the same thing for the y direction, and I get two different masses. I get a conservation of momentum in the y direction and the x direction. It's not a perfect situation. The video is terrible, so I'm doing the best I can. Okay, so but that's how we can do this. It's kind of cool. Let's talk about actual video analysis. So there's my conservation momentum talk. If you have not done video analysis, there's a couple ways to do it. I like to use Tracker Video Analysis. It's a free program online. There's also Verniers Video Analysis. It's very good too. I've used this one more, so this is what I use. So in this program, this is a screenshot because I tried to do it live, but it turns out that it was kind of troublesome. So the idea is you drag your video in here. I set the scale. There's my scale right there. And then I mark the location of the object in each frame, and then I do that for the other object too. So here I have two objects. There's my missile, and then there's my orb. And I didn't mark the orb before because it was right there in the center of this X right there. That's where I set my coordinate system to. I assume the coordinate system stayed true to the motion, even though the orb left it. So I'm measuring relative to that. I'm assuming my reference frame stays constant, which is clearly not the case. Okay. So I get this data right here, right? I get my, here's the orb, the Y and X position as a function of time, and we can see how things go. So let's look at the data after I click. I'm not going to click through the whole thing because it just gets tedious and boring. So if I do that, look at the missile, the motion of the missile before and after, you'll see right now, here's the X motion, and the collision happened right here around 0.8. So the velocity of it beforehand, it does turn a little bit. I want the velocity right before the collision, so I actually took these data points right there and I fit a best fit line. So Tracker Video gives me this coefficient right here, 3.2 E1, so that's 32 meters per second squared. And again, remember, I scaled it based on that missile, which may or not be true, but it doesn't matter. And then after the collision, we would look at this part right here. Okay, so I'm going to show you those values that I got right there, but you can do it on your own. And then this is the Y direction. Again, I'm looking at before. I'm fitting just these data points. It clearly changes in the Y direction much more. And then after it changed again, so I used just some of those values right there. You got to know kind of where it was that it collided because it's not clear. In a normal collision, you would see a nice bend in the position graph to show a before and after velocity. Here's the missile. Oh, this is the fit after. So after the missile hit, I have 43 meters per second in the X direction and negative 11 in the Y direction. And then if we do the same thing for the orb, here's the orb. Now the orb is kind of difficult, right? In the X direction, it's this part right here. So I get negative 11. And then the Y is really, so right here is the collision at 0.8. You see that it didn't really do too much in the Y direction. So I have some small value here. I have negative 0.2. I actually redid that and got a little bit higher value that I'm going to use. So those are straight from Tracker Video Analysis. So here's the data that I got, and I'm going to show you. I'll show you how to get these calculations. So I have the velocity of the missile before is 32, negative 15 in the XY direction. I'm assuming everything is in the XY direction. Z would be up and down, and there's no Z motion. And then after 43, negative 11, and then the collision, see, I changed that to negative 1.3. So there you go. And then I get two different masses for my calculations. I'm going to redo the calculations for you. So in the X direction, I get 45, which, I mean, that's not very heavy for an orb. And then 138 in the Y. And of course, there is some motion after that where it corrects, and so there's another external force. But I think even with these terrible numbers, I think it's pretty clear that this is not like, it's not a human-powered aircraft. It's too small. I mean, the mass is definitely, if you said anywhere between, let's say, 4 40 and 500 kilograms. I mean, that's not big enough to be a plane, right? It's not an aircraft. It's something different. It's smaller. The size is too on the order of a Hellfire missile, which we can see. Okay, let's. I'm going to go ahead and show you one more thing. This is another view they have. If you want a homework problem, this shows the. I thought it was a video. This shows there's an external view of the orb that you can see the water in the background, and you could use the water as your reference frame to measure the speed of the orb, and then use that to calculate the collision or scale the collision, assuming you know the speed of the Hellfire missile. It has a max speed of 450 meters per second. I don't know how fast it's actually going to that point. So there's a lot of confusion there. But this is just really, I'm not really answering the question. I'm just playing around with physics and Python. Okay, so I'm going to do a couple cool things over here with Python for you now. One of the things I like to do is once you get that data from Tracker Video Analysis, I can import that into Web v Python, and that's what I've done right here. So I have values, I have X values for the missile, I have Y values for the missiles, I have X values for the orb, and I put them in these lists right here. And I just copied, what I did was I copied them from Tracker, and then I posted them in a text file and removed the returns and added commas so it could be a list. So this is a list of all the data right there. And I added in zeros for the orb beforehand, even though I didn't mark those, so that they're the same length list. So right here I have my velocities before and after the collision, and for the orb, and there's my mass. I used 45 right here, but that's fine. So let's calculate the X mass. I'm just going to show you how to do that because it's kind of nice. Mass of the orb in the X direction, which seems kind of dumb, but that's what that is. It's going to be the mass of the missile, which I'm calling H for Hellfire. I changed things up. Now I need the X component. So this is going to be Vm1.x. If I write this as a vector, then I can access just the X component of that. It's 1 minus 2, yeah. Minus Vm2.x, and then that's divided by V orb x 2.x. And then let's print that. Print MOX, and then put units of kilograms. And let's do the same thing for the Y. MOY is going to be mass of the missile times the velocity m1.y minus velocity of the missile 2.y divided by velocity of the orb 2.y, and let's print that. MOY equals MOY kilograms. And then I run it, and that's how I get those values. Now, here's the fun part. I can actually use the data to animate the whole situation, which I know where I have the animation, but we're going to do it anyway. So this is kind of fun. Okay, so let's do this. Let's make two 3D objects. Let's make a 3D missile and a 3D orb. I'm going to draw them both as spheres, although if you wanted to, you could mark the front and end location of that missile in the video, and then you could get the orientation. I've done that before. It's kind of fun, but I'm just going to draw the missile as an orb here just because I don't want to have too much fun. So let's make our two objects. So I'm going to say the orb is a sphere. Its position is going to be the starting position of the orb in the thing, which is 0, 0. So it has a vector 0, 0, 0. I need it to have a radius. Let's give it a radius of, let's just say 1 meter. So that'd be bigger than the Hellfire missile has a length of 1.6. So this has a diameter of 2 meters. So about the same size though. Let's give it a color cyan, because that's the color of an orb. I don't know if you knew that is. And then make trail equals true. So it's going to leave a trail. Now let's, the missile I'm just going to call miss. I always misspell missile, and I'm embarrassed to say that, but that's the truth. Position, now the position for this, I'm going to use the position of the missile. I have these lists up here of XHS and YHS. So the position is going to be the vector X, which is what is that called? call it XHS, but I want to index the first element, so that'd just be the 0th element, and YHS, 0th element, 0. Then let's give it a radius of 0.8, right? So it has I'm going to give it a diameter of 1.6 meters. Its length is 1.6. Color is color.yellow. And make trail equals true. Okay, let's just run it, see if things are looking right-ish, and then we'll make it animate. Okay, so there's my missile. Oops. So there's my missile. That's my missile, and that's my orb. Okay. So now we're going to animate, and we have this time step in there, but I don't really care about the time step. I don't even need to make this run in real time. I'm just going to make it run. So we're not going to do an Euler calculation where we use initial conditions to find future things, because I know where they are. I'm just going to animate what I have. So let's do this. For I in range length of XHS. So they're all the same list, right? So this I will go through each element in one of the lists, but they all have the same number of items, so we can do that. Next, I'm going to say rate 50. So I'm going to do 50 loops per second. I don't even know what that really should be. That's what I'm going to do. Now all I need to do is to move my objects to their new location. So orb.pos is going to be equal to vector. What was the orb called? It's called xorb and yorb. So xorb I, the ith element of the xorb list, yorb I, the ith element of the x list. That's it. I moved it. Now I'm going to do the same thing for the missile. Miss.pos is vector xhs I, yhs I. 0. And I don't need to increment anything because it's already done that in the for loop. So this should animate the objects. It will give us some insight into how they move because it leaves a trajectory and all that stuff. Okay, so I want to go a little bit slower. So let's go a little bit slower. Let's go 20. It did look cool though, didn't it? Okay. There you go. And you'll notice some weird stuff here. I mean, why is that curving? So if the whole thing is moving this way, I'm not actually sure why it's curving. I think it would have curved the other way. There's definitely an air resistance acting on these things. I don't know about the steering mechanism on these things. Again, not a weaponologist. But we're looking at this collision right before, right after. Clearly, it gets pushed to the right, and that means the orb is pushed to the left. This is in 3D, so I can rotate it around, right? So that's kind of cool. I just think it's cool to animate. I'm going to run it one more time. That's pretty cool. Okay, so if you want to make your own animations, I will give you a link to this code. It has that data in there. Of course, you can get the data yourself too. So now you think about what homework questions could you have. Number one, use that other reference frame to get a speed of the orb and the velocity of the frame. And here's the fun part. Okay, animate this down here. I'm not going to do this. You can do this though. Animate this to down here. Now, right before the collision, stop using the data and switch over to an Euler calculation and let there be a collision between these two things and see what happens. And then so kind of work backwards, right? We use the collision to take to find the mass, but assume you know the mass and see what kind of collision you have. So I will link to below a video on numerical collisions. The basic idea is you let these two things overlap a little bit with the spring pushing them apart, and that conserves momentum and everything. That's kind of cool. So that can be your homework if you want, if you need some homework. And again, this I'll link the video I used. It was from Time's YouTube channel, but you can do that. I will link this Python program down below so that you can get the data if you want it. And then I said there'd be another thing. Oh, the collision. So it's 3. Don't let me forget 3 things I'm going to put in there. Okay. If you have more data on this orb, like I don't know if all the parameters of the video, then maybe we could get a better analysis, and I'm sure someone has already done that. But it's a fun physics problem, so that's it. I'll talk to you later.